this course by Jakub Vosmera, who is our great postdoc, who did his PhD in Prague and then went on to the first postdoc at ETH, and then finally came here. And yeah, there'll be 3 lectures on string field theory. First lecture, obviously today. Second lecture Wednesday this week, and the third lecture is going to take place in 2 weeks on Monday. Without further ado, Jakub on string field theory. Anyway.
So many thanks, Dalmo, for the introduction, and also for the opportunity to do this course. So let me start by going through the rough plan of what I have in mind of telling you. Roughly, I was thinking originally about dividing the course into 3 parts, where in the first part I wanted to tell you what SFT is and why we should think it is important to learn it, and then of course go through the basic details of constructing the string field theory action, starting from the free part of the action and then all the interactions, and then giving you examples of some simple classical solutions. Then in part 2, usually in virtue string theory, we think about CFTs as tools. That is, we typically take a 2D CFT and use it to tell some interesting things, compute some observables in string theory. So now with string field theory, I will show you that we can actually also go the other way around, and we can use string theory to derive or to show some interesting results about 2D CFTs. So that was the plan for part 2. And then in part 3, I just wanted to give you a quick taste, quick gist of what has recently been happening in string field theory. But having said that, so let me confess that I would ideally like to go very slowly, especially over the first part, where I aim to give you some basic introduction to SFT. So that will probably have an effect that this part 1 of the course, I like to go very slowly and pedagogically, will spill over well into the second lecture. So that in effect will probably cause that there will not be much time left for this third part. So for the time being, I will put it in brackets. But at the same time, you can think of these applications of string field theory into the conformal field theory as very well as an integral part of the recent developments in SFT. So justice will be served in either way. So I hope this is it is much better to go slowly over the introduction without rushing, rather than trying to go very quickly and do this part 3. So maybe in the future I can give some general club about the recent progress. That said, let me start by going over a few resources which I found very useful in preparing these lectures, and which I hope you will also find useful when trying to learn more than I will try and tell you. So first of all, in general, there is this very nice and very recent review by Schocks and Barton's feedback. It came out last year, and really this is the I would say the most useful resource which I found for preparing this course. So then there is a book by Harold Urban about string field theory, which does not contain only string field theory. It also discusses in quite some detail the basics of the Birch formulation of string theory, and also of 2D gravity. So then finally, if you find yourself to visit, you read this review, which has about 150 pages, or this book, which is about 300 pages. There is this very short review by Karel McAfee, which is only 30 pages. So that is very nice and concise. So then more specifically, for the string field theory describing closed strings, closed string field theory, there are these 4 lectures by that arrow, and also this a little bit longer review by Corinne de la Cura and company, which also discusses some applications of closed string field theory in string theory. So then finally, if you're interested in some details about describing open strings and also constituent solutions, there is this very nice review again by that arrow. These are another 4 lectures, this time on analytic solutions in open string field theory. So now let me start with part 1 of the lectures. That is the introduction. First of all, let me try and give you some motivation as to what roughly string field theory is and why we should care about it. So I think it's correct to say that string field theory should be thought of as a quantum field theory for string theory. In the sense that SFT is in the same relation to string theory as the usual quantum field theory would be in relation to quantum mechanics for particles. We can also say that that this is an off-shell theory for strings. So in the usual kind of on-shell first quantized approach to string theory, what we usually start with is a worksheet sigma model, which we quantize. Right? We fix the reparameterization of symmetry. We can do so in many other ways. The way which I will choose later in the course is the BRST quantization, where the end point of this procedure is a worksheet conformal field theory, within which we can identify a particular class of states which we call physical states. Physical string states. So then, in the worksheet approach to string theory, we can go directly from the physical states, following the usual prescription of computing some correlation functions on a Riemann surface and integrating these correlation functions over the moduli space of these Riemann surfaces to directly obtain on-shell string amplitudes. So now the idea of string field theory is to go a little bit longer way. So given the physical states, which should be roughly thought of as particles, to each of the physical state we associate a string field. So this direction is going off shell. And as in the conventional quantum field theory for particles, these string fields should be thought of as living on the space-time, on the target, on which the string propagates. So now, given these string fields, we will aim to formulate an action for these string fields, which will be the action for string field theory. And we will try and do so in such a way so that the Feynman rules given by the vertices of this action and the propagators will reproduce what we call optional amplitudes. So I will later in the course spend some time introducing these optional amplitudes, telling you what they are. So in particular, they should be thought of as generalizations of the on-shell amplitudes. So at this point, when we then restrict the external states to being back on shell, we should be able to recover the on-shell amplitudes which we would have obtained by following this direct prescription of the Verchi string theory starting from physical states. So now, of course, you can ask the obvious question: why should we go this longer way? Why it is not enough to just start with the physical states without ever going off shell and compute all the observables which you like by just following the usual Verchi prescription? So now I will spend some time telling you many reasons why it is good to go this longer way, and why it is actually not always enough to follow this prescription of integrating over the moduli space. So first of all, let me start by telling you something which may sound a little bit provoking, and this is that this prescription may not always be well defined to give us finite answers where we expect to obtain finite answers. So in particular, there are many ambiguities with following this prescription, and many of them have a common denominator, which are IR divergences. So let me give you a couple of examples where these IR divergences arise, and to be very concrete and to stay at a very simple level of discussion, let me consider the simple cases of 2-to-2 scatterings, that is 4-point on-shell amplitudes. So even at tree level, one finds that this generic prescription for computing on-shell amplitudes generally only works when the external states are allowed to have generic momentum. So to give you an example where we encounter an IR divergence at specific momenta, let me draw the following Riemann surface. So this Riemann surface is supposed to be a Riemann sphere with 4 punctures, at which I'm inserting on-shell states with momenta k1, k2, k3, and k4, which are on shell. And this kind of a very thin neck in the middle is supposed to describe the Riemann surface near its degeneration, where the Riemann sphere becomes actually 2 Riemann spheres which are connected by a very thin long tube. So this I schematically draw as such a pinching degeneration, but you can really think of this as being conformally equivalent to 2 Riemann spheres connected by a thin tube. So in this region of the moduli space of this 4-punctured sphere, this this amplitude can be clearly represented by a Feynman diagram where I have K1, K2, K3, K4 at the external x, and some momentum K propagating in the middle. And for generic choices of K1, K2, K3, and K4, this propagator, this momentum K, in the propagator will be off shell. So this is fine. But now, when there are massless particles in the theory, I can in principle choose one of the external momenta, let's say K4, to go to 0. So let's see what happens then. If K4 goes to 0, then by momentum conservation, K becomes equal to K3. But K3 is on shell. And since we know that this propagator in the middle, I mean in a completely generic theory, should go roughly as K4, sorry, K squared over, 1 over K squared plus M squared, you see that in the case where K4 goes to 0, this propagator is forced on shell, and we obtain a divergence. But at the same time, we know that there are situations where we would exactly like to put one of the external states at 0 momentum. So these situations are precisely when we are trying to take the background which we are starting with and deform it by adding some marginal interaction to the action. Where the marginal interaction is precisely represented by the 0 momentum external state. So we know that the 0 momentum insertions we would like to interpret them as computing an amplitude. So in this case, it would be a 3-point amplitude, but on a background which is deformed by inserting a 0 momentum marginal state. And there, of course, we expect to obtain a finite answer. So this is not good, right? So we will see that in string field theory, we'll be able to exactly deal with such kind of situations, because in string field theory, we should be constructing the deformations of our background as classical solutions. So following that prescription, we will realize that around the different background, what we should actually do, we should rethink what our physical states is. So around the different background, we will see that the masses of the physical states will regenerate, receive some corrections, which of course we naively didn't really assume here. So here we are trying to construct the amplitude around the different background using the physical states of the original undeformed background. So in SFT, we will see that there will be an exact description of making sense of that computation of the amplitude around the different background in such a way so that we obtain a finite answer. Yes?
Are there backgrounds that I can't obtain by deforming around a given background? Is it a connected space?
Yes. So the solutions which we will have in mind and which I will construct explicitly later in the course, these are the solutions for marginal deformations. So they will depend on a continuous parameter. If the marginal deformation is not obstructed, if these moduli of the background do not receive some potential, right? So then the string field theory will be able to obtain a finite region of the moduli space around the point which we are expanding. So this was an example of an IR divergence which you would have obtained in the usual Verchit approach. even at tree level. But then, when we go to the loop level, situation gets even worse. So there, you'll see that we can get IR divergences even at generic momentum. So for that, let me draw the following Riemann surface. So this is again an amplitude of 4 on-shell closed strings. This time at 1 loop. So this is represented by this handle here. So again, this region here should be thought of as a very, very long thin tube where closed string propagates. So you can again see that this is to be associated with a Feynman diagram of the following form. Let's draw this a little bit longer. So now, at this point, you can see that from momentum conservation, the momentum which flows through this propagator is again k1, while the momentum here is again some generic k, which is given as k1 plus k2. So here, even at a generic on-shell momentum, you can see that this propagator, following this slope on the external leg, is forced to be on-shell. So that again gives us an infinity. So again, we can ask ourselves why are we getting this infinity in the usual worksheet approach? And the reason is very similar actually to what I was describing before in the case of tree level. That is that we are naively trying to use the on-shell states which are on-shell classically at tree level to compute the loop amplitude. But using the usual intuition of quantum field theory, we know that when we try and go to loop level, the masses of states can get renormalized, right? So this is of course something which has to be taken into account also in string theory. Let me draw another unhappy face. So not only the masses but also the wave functions can get renormalized. So we will see that when we have string field theory at our disposal, there will be again a well-defined prescription of dealing with this problem, which again you can already guess if you know some basics of QFT. So we know that in QFT what we would have done, starting from the classical action, what we would first do, we would formulate the 1pi effective action, and then of course we could construct the 1pi propagator. From the 1pi propagator, we could read off the poles of the renormalized states and also the residues of these poles, which would give us the wave function renormalization. And then using this renormalized spectrum, we could get finite answers from perturbation theory. So provided that we can get a quantum field theory formulation of string theory, we could just do the same and get finite answers. So now let me give you one more example of an infinity, which we cannot simply deal with using the first quantized on-shell worksheet prescription. And for that, I will draw the following Riemann surface. Again, I will have one handle, but this time all the on-shell insertions will be in this other part of the Riemann surface, so that you can interpret as a diagram with this tadpole in the middle, right? So again, the momentum here will be just k, but the momentum here will be 0. So then you can see that as soon as the theory contains massless particles, which of course can be at the same time on a shell and have a 0 momentum, which of course in string theory you generally have massless particles, you will get an infinity. So then again you can ask yourself, why are you getting this infinity? Well, what is wrong with your logic? And the thing which goes wrong here is that if you have tadpoles in the theory, that means that that your vacuum, which was the true vacuum at tree level, is no longer a true vacuum at a quantum level. In other words, the classical vacuum through these tadpoles will receive quantum corrections. So, to actually illustrate what I've just said, let me go back to a very simple example of the phi cubed theory. And this, at the same time, this will tell us how this problem can be resolved in a field theory language. So, considering the phi cubed theory, you can start with the classical action and compute the 1pi effective action. So that will roughly look the same as the classical action. So we will have a kinetic term. And the cubic interaction. But then, through loop diagrams, we will also generate this dipole term, which is linear in the scalar field phi, plus some corrections to this phi squared. So, taking this action and varying with respect to phi, we can obtain the classical, or in this case, actually 1pi equations of motion for this field phi. And what we will discover is that phi equals 0, which we were naively thinking would be the vacuum at tree level, is no longer a classical solution to the equation of motion. Right? So phi equals 0 is no longer a solution, precisely due to the appearance of this term, which is linear in phi. So then instead, in order to be able to make sense of perturbation theory in the usual sense, what we have to do, we have to re-expand the action around something which is a classical solution to the 1pi equations of motion, which in this case amounts to expanding this field phi around this value minus 2c square root plus some corrections which will come due to these terms which are higher order in field phi. So this will be the new quantum corrected vacuum for the phi cubed, plus some new fluctuation which I don't with psi. And then when we do perturbation theory in psi, we should recover again finite results. So following the same logic as in this simple phi cubed example, if we look at the 1pi effective action for string field theory for generic backgrounds, what we should generically expect to obtain are these linear terms which arise at loop level. And the way of dealing with the resulting IR divergence is exactly the same. We have to find a classical solution of the 1pi equation of motion in string field theory, which identifies the correct vacuum around which we should perturb. So the IR divergences are certainly one good reason why to why to try and obtain a field theory action, or why to obtain a field theory formulation for string theory. And another good reason are the non-perturbative corrections to string amplitudes, which in string theory arise due to the so-called instantons. So as we know, the amplitudes are generally given by a path integral. So these path integrals, they generally receive contributions not only from the perturbative regime, but also from saddles, from classical solutions which have finite on-shell action. So in particular in string theory, these saddles with finite on-shell action, they are given by the branes, which have no non-compact Neumann directions, which are always the Dirichlet, which are not extended in non-compact space-time directions. So these d-branes we call the instantons, and there is a special case of the instanton, which is the d-1 brane, which is Neumann in all direction. So in general, some of the directions can be compactified. So if the d-brane is a Neumann object along this compactified direction, it will still have finite on-shell action, right? It will still have finite mass. So these in general will also contribute and will give corrections to the string amplitudes. And there is also the special class which is Dirichlet in all directions, and these are just the d-1 branes. So in general, these will give us corrections of the order e to the minus a over g string to the co-string amplitudes, where a is precisely the value of the on-shell action. And the way how we would compute these contributions is, on top of considering the worksheets which are just Riemann surfaces with block punctures, which we do for the usual co-string perturbation theory, we also consider worksheets with boundaries. Where on these boundaries, we are choosing precisely the boundary conditions which correspond to these d instantons. So let me draw an example of such a surface. So again, this is going to be a Riemann surface with some genus in general. Some punctures representing on-shell co-string insertions. And now, to represent the boundaries, I want to cut out some disk-like regions which will create holes in the surface of this Riemann surface. So these are the objects which we like to compute in order to obtain these d-instanton corrections. Now, if we will go and try and do so, we will discover that these amplitudes, they are really suffering from heavy IR divergences. Again, so again we have ubiquitous IR divergences. So to showcase how these IR divergences arise, let me consider a very simple example where we just have one boundary. So in the case of one boundary, and for the sake of simplicity, let me also consider the zero genus, the Riemann surface becomes precisely a disk. So again, let me consider a special class of disks, a special region in the moduli space of punctured disks, where I have a degeneration. So now, this is a little bit different picture than I was drawing before. This thing is really supposed to be, let me draw it actually in different color. I've used blue for the boundary there, so let me also use blue for the boundary here. So this curve is supposed to represent the boundary of the disk. And this pinching degeneration here is now not to be associated with a propagating closed string, but with a propagating open string, because this is supposed to be conformally equivalent to a very, very thin strip of Verchi. So this is now open string. Degeneration. But then you have to realize what the spectrum of open strings on the instanton is. And in particular, when it comes to the non-compact directions, since the instanton is supposed to be Dirichlet in the non-compact directions, it means that the spectrum can never support a finite momentum. All the states, with respect to these non-compact directions, all the states in the spectrum, they have to be zero momentum, right? So as soon as there are massless states, which in general there are, right? Because the instanton typically has many moduli. In particular, in the non-compact direction, you can just shift the instanton any way you like, so that will generate a moduli space. So that means that there will be in general massless zero momentum open strings propagating in this channel, and that will again give us an infinity because the propagator will go up. So, so trying to compute these kind of contributions to the closed string amplitude is using the usual Verchi prescription is doomed to fail. So then again, we can ask ourselves, in what way the string field theory can help us to perform this computation, and the answer is as follows. So as soon as we have a field theory formulation for this problem, we can choose to do the following prescription. We can choose to do the complete path integral computing this amplitude, except for the massless states which are supposed to propagate here in this channel. So first of all, what we compute is is almost an amplitude, but without performing the path integral on the massless states, on the open string massless states which are propagating here. So that is, of course, supposed to be finite, because as long as there are massive states propagating here, the answer is not going to be plagued by II divergences. Right? But then, of course, in order to compute the amplitude, we're supposed to integrate over all the string fields, right? So what should we do? Now the key point here is to realize that these massless states, they are precisely in one-to-one correspondence with the moduli of the d-instanton. So so instead of performing the path integral over the massless fields, what we do, we will evaluate this amplitude, this disk amplitude, without performing the path integral over the massless fields at a fixed value in the moduli space of the d-instanton, and then in the end, with a suitable measure, we can integrate over these moduli, and that should give us the correct answer. And using the correct prescription of string field theory, the answer turns out to be finite. And in a particular example, so for instance, type 2b string theory, where we know what the answer should look like, because we know that type 2b string theory should manifest the S-duality even at the level of the closed string amplitude, we can check that the answer which we get from string field theory is indeed correct and in line with these expectations.
In the string field theory picture, is S-duality not manifest until the final answer in general?
Yeah, so depends what you ask. I mean, if you ask about the string field theory action, Yeah, that, I mean, at that level, the S-duality is not manifest. Yeah.
So, is there, just to take a concrete example, in the past several years, people have been studying the structure of worldsheet integrands in string theory and finding various these modular graph forms and lots of nice SL2Z invariant functions and forms. Is there a string field theory way to find those functions that mean anything in string field theory?
Well, I wouldn't say there is an independent way of finding these results. I mean, of course, when you have your string field theory, you can draw Feynman diagrams. You can compute the amplitudes, and taking the external x to be on shell. I mean, you basically recover the same structure as you would have obtained from the first quantized prescription. Yeah, but all these all these subtleties with the IR divergences, they kind of come automatically from the string field theory calculations. So that's the only advantage which you get over the first quantized prescription. But I wouldn't say there are any known independent insights as to giving these structures which you are describing.
I guess in particular because their structures the integrand. So.
Yes. Yes, it's just the integrand, yeah, which is not really like an invariant notion in string field theory. Yeah. Okay. So let me continue with giving you a couple of more reasons why to do SFT before actually introducing the action of SFT.
May I ask whether somewhat conceptual question while you're
Sure.
So, as you said, you're about to tell us soon will tell us the action.
Yes.
And motivated SFT is like QFT for strings.
Yes.
And now we know that many, possibly most QFTs don't have an action.
Yes.
Is this aspect of string field theory supposed to be the first step towards something bigger, or is it just the analogy doesn't quite extend that deeply?
Well, yeah. Yeah. Having said that, I will give you an action for SFT, and actually that connects to what I'm going to talk about now. The action for SFT, although it is supposed to be so-called background independent, right? So as I will tell you, that basically means that given an SFT action around any given background, we should be able to see any other background by expanding around the classical solution. That background independence is far from manifest at the level of the action. So maybe this is not the most fundamental formulation of the non-perturbative string theory which ever exists. And having said that, right, if there are these backgrounds which we're describing, which cannot be described by an action, those backgrounds will most probably be somehow missed by this background independence prescription of SFT, right? Because if I say that I can obtain any other background by expanding the original background which I start with in a small fluctuation around the classical solution, that is saying that the background is described by an action, right? So if there is a background which cannot be described by an action, I will probably not be able to find it using it, in this way.
Yeah, that's connected to the previous question. So I guess I was wondering, like, if there's some independent principled proof that actually the space of solutions is connected. I would have been very surprised if the answer were yes.
There is a proof for open string field theory.
So like without string field theory, just the space of things the string theory is capable of describing, the space of solutions is somehow connected, so that all you need is an action. Sounds like there's no such proof of that deep statement, but so at least string field theory can reconstruct some of the backgrounds and maybe not all.
Yeah, I think that's that would be like a careful way of phrasing what the string field theory trying to achieve. But still, that space of backgrounds may be very, very big and may very well contain backgrounds which we don't know about and which we wouldn't be able to discover using other methods, right? So precisely, let's talk about background independence. In this kind of restricted sense, which we were just discussing with Eric, so the situation in the first quantized Verchi string theory is that in order to be able to compute the amplitudes, we need to first fix a background. We first need to fix a consistent critical background for the propagating string. And then, having fixed that background, what we can do is basically only to compute the observables for that fixed background. So in SFT, the situation is much richer than that. So let me just put down on the blackboard what I've been saying, and that is that classical solutions of string field theory should be thought of as other consistent string backgrounds. So to give you some examples, again going back to what I've already discussed to some extent, there are the marginal deformations. Which arise whenever the background around which I formulate my string field theory contains some moduli. So then what I can do, I can construct a family of classical solutions of string field theory, which will describe precisely the way I can move around the moduli space and thereby obtain some other related string backgrounds. Then I can construct other classical solutions. For instance, the ones which we usually call tachyon condensation. So that is just a fancy string theory name for what would have been relevant deformations of the Verchi CFT. So this is precisely how in string field theory we can make sense of tachyon instabilities. So whenever I construct a string background which has a tachyon in its spectrum, that should be thought of as being a sign of that background being unstable, right? So then you can ask, what happens if I introduce a small perturbation in this unstable direction? I mean, what is the endpoint of the flow which I trigger in this way? So string field theory is precisely well suited for addressing that question. You can precisely start perturbing the string field theory action in that direction and see what kind of classical solution, what kind of RG fixed point of the Verchi CFT we flow through. So then, of course, you can hope that whatever pair you land at, that would be stable with no tachyonic instabilities, or it will not, and you will have to flow again and again, right? Yeah. So one thing which I would like to note is that what I've written here is that classical solutions of string field theory should correspond to consistent string backgrounds. But no one tells you that these consistent string backgrounds should be associated with Verchi CFTs. And indeed, there is expected to be a huge class of consistent string backgrounds for which you cannot write down a worksheet CFT. An example of that would be a background containing NS5 brains, or in general, some ADS5 cross S5 backgrounds with Raman flux, right? So there's the famous problem of trying to formulate something which would be a worksheet description in the background of non-zero Raman flux, right? So here you can immediately see a possible advantage of having a string field theory formulation at our disposal. So it may very well be the case that although these backgrounds which I have just talked about may not have a worksheet description themselves, it may very well be the case that they can be obtained as classical solutions of a string field theory which is formulated around a background which does have a worksheet description, right? So then this tells you that there could be an indirect way of extracting some interesting physics of these backgrounds with no worksheet description, and that is by starting with a background which does have a worksheet description, formulating a classical solution, then expanding in small fluctuations and doing perturbation theory around that classical solution, which is supposed to represent, let's say, a NS5 brane. Right. So let me put that down. Background without a worksheet description. So in that case, for those backgrounds, of course, we do not know what to do at all in the usual first quantized worksheet setting. So we can try and represent them as SFT solutions around a background which does have a worksheet CFT description. And indeed, recently there has been a lot of progress in that direction. That was started in 2018 with a paper by Sheen, Scott Collier, and Minjacho. We're precisely trying to implement that idea of constructing or of describing the physics of ADS5, which is 5 backgrounds with non-zero Raman flux at large ADS radius, starting from plot space in the RNS description. And even more recently, they have achieved a complete construction of the solution representing ADS5 cross S5 from plot space. So this is a work which is to appear very, very soon by Minjacho, Joao Gomide, Jaroslav Scheinflug, and Sheen. So I will invite us to look out for that paper.
I mean, we'll see.
Yeah, you'll see, but yeah, in particular, they construct, I think, in principle, to all orders the deformation of the flat space in RNS, which constructs ADS5 cross S5 at finite value of the radius. So yeah, I think that's the stage at which they currently are. But then their objective is to expand around that solution and compute some amplitudes to recover some Rorschach amplitude in ADS5. Yeah, basically using flat space variables. Yes.
So this is related to the IR divergences that you were discussing. So you do stationary particles, you sort of know that these IR divergences, they exponentiate, and they are not relevant for observables. So do you expect something similar to happen to these things for the IR divergences?
Yeah, I'm not sure. As I was trying to describe, all the IR divergences which appear in the conventional string perturbation theory, they can be traced back to us doing something which is not entirely correct, right? Either to scattering states which are physical states at tree level, and not taking that into account in normalization, etc., etc. So I think these are a little bit different kind of IR divergences, which are more connected to our ignorance than to something physical. Yeah, I mean, I think most, or at least some of them, they can be thought of actually as UV divergences on the word sheet, right? Yeah. I mean, when I say IR divergences here, what I mean there are like IR divergences in space-time, right? But on the word sheet, you can, for instance, see that if I take this surface near to its degeneration, what that means is that I'm separating two punctures from the other two punctures, so that is as good as having a collision of these two punctures. So that would have been a UV divergence on the word sheet, right?
So here, like, once you have renormalized those UV divergences, you don't need the operators in the effective action. Say you got 2 loops, 3 loops, they're so will be finite. You still have to
Right. So yeah, I mean, what you do in the string field theory language is the same as what you would have done in QFT, right? So you have to compute the complete 1PI effective action, which I mean, will in general receive contributions from one loop, two loop, etc. So loop by loop, you have to consider, let's say, contributions to the mass renormalization, wave function renormalization, etc., to the vacuum shift. And if you do everything correctly, consistently, you should be able to obtain finite answers loop by loop.
So, for instance, like in the standard model, you don't have to introduce infinite counter terms, right?
Yeah. Yeah, that's true. Yeah. Okay. Yeah. I have to think about what the best answer to this is. But yeah, I don't think this is suggesting that that 1PI effective action formulated from string field theory would not be renormalizable or something like that.
Okay, this discussion of background independence and living in the space of solutions again. There's some implicit statement that you can integrate up the perturbation theory. Will this be clear when you write down the action, or does one have to work to prove that? What's the status of that?
Sorry, can you repeat the last part of the?
If I make a marginal deformation and I work perturbatively, then yes, I can really move a little bit.
Yes.
Move more than a little bit. Is it clear that I can do a non-perturbative resummation of this procedure and actually get to a bona fide new background?
Yeah.
And what does that rely on in the structure of the action?
Yeah, that actually depends on the particular string field theory which you are considering. So in the case of the open string field theory, you'll see that we have a complete formulation of the action at our disposal, which in the bosonic case is just cubic. It's the written OSFT. So there, I think people have been trying to make statements about resummability of the perturbation theory, and yeah, actually, what I found is that the answer also depends on the choice of gauge in which you are trying to construct a solution. So there are choices of gauge in which SFT is capable of reaching on a finite region of the moduli space, but is not able to reach an arbitrary point in the moduli space. But I think the state of the art is that people expect the SFT to be able to reach also finite distances from the background which you're starting.
I'm afraid I'm asking the same question as before, I guess. Is it possible that this is the same question, that there are parts of the space of solutions that one cannot actually access by way of integrating perturbation theory?
Yeah.
or transcend the use of the action and require something like resurgence for string field theory or whatever I should call that.
Yeah. Yeah.
Sorry, if I understand it right, the space of we should make a distinction between the connectivity of the space of fields and the connectivity of the space of solutions, right? So of the equation motion. So if I understand right, the string field theory is certainly capable of describing classical solutions which are disconnected from the point where all the fields are set to zero, right?
Yes.
So in a sense, the non-perturbable existence of some solutions which are disconnected has nothing to do with the question of summability of some perturbation series, right? You've got some equations of motion which you can solve if you find some point which is disconnected. And you cannot reach this by acyclic marginal deformation, but string field theory can describe this point. Is this understanding correct?
Yeah, that's true. Although it is, although I mean, such solutions are very rare. I mean, when you come to actually, analytically constructing these solutions, I mean, many of these solutions, I mean, have been constructed numerically. But then again, you can ask a question if the numerical solution to the equations of motion, which is constructed by truncating the solution level by level, if it converges or not, right? But but then there are examples. So there is a famous example of the tachyon vacuum in open string field theory, which is a solution which is non-perturbative. It is not connected to phi equals 0, right? And at the same time, it was proved to be a good solution of FSFT equations of motion. Yeah.
Okay, so I guess the conclusion is that even if the space of consistent backgrounds of string theory is disconnected, this is not an obstruction for string field theory to be able to describe that, right?
Yeah, right. Yes. On the other hand, some of the promise here seem to be that you can start from one background and go a long way. But then that's, as you pointed out, a logically distinct question from being able to enumerate the complete set of solutions to these equations. So, but it was if it turned out that you didn't have to do that, you could just know a few of them and then reach some perturbation theory. But it sounds like to understand how much of the space you can access, well, we don't know the answer because we don't know how big the space is.
Right.
Okay. Yeah.
Shall we take a break?
Yeah, I think this is a good point because now I'm about to start the construction of the action.
So it's 11:07. Let's take like a 10-minute break. So let's meet again at 11:20.
Perfect. I'll keep the Zoom. I'll keep the YouTube broadcasting active, so you guys